Good morning to all students. So yesterday we have left up to here. We have gone through the root locus of this transfer function, and we have used this characteristic equation to find out the value of k, which is from 0 to 6. Okay, so now we are going to check for different values of k the root locus or the stability. So you know that root locus gives an idea about the poles of the closed loop transfer function. Okay, that is this characteristic equation, roots of this characteristic equation. So the root locus is helpful in designing the value of k, that is gain of the proportional controller. So we can select the value of gain by using the root locus for p controller. So this system in figure 1 is stable for different values of k from starting with point 2, which is greater than 1, which is greater than 0, then 1, then 5.8. Okay, these are minimum values, okay, to which the k will be stable. So but there is a question arising that what value we should select. Okay, now we are going to analyze the value of k for different these values. Okay, we have to check the stability and steady state error. Okay, so basic logic is that the value of if the value of k will be high, for example 5.8, this is the highest value, which is less than 6, then it will reduce the stability, but this is a disadvantage. But also it will improve the steady state performance of the system, which will be an advantage. So we have to select the value appropriate, which makes the stability also less steady state error. Okay, so now you can see this kp, okay, is formulated by limit s tends to 0 k g of s h of s, okay, where steady state error is ess equals to 1 upon 1 plus kp. Okay, so it in case of step input this is possible. In case of ramp input this equation is applicable. Okay, and in case of parabolic input this is done. Okay, I think you have already learned this in case of steady state analysis or time response characteristics of a closed loop system. So it can be observed that for a high value of k, values of kp, kv and ka will be high and steady state error will be low. Okay, so now example, take value of k as 0.2, the minimum value. So in this case the characteristic equation you can see it here. So in case of k we will write 0.2 over here, and roots of this equation are, after finding out this by using solving this by synthetic division, we can find out the roots, that is minus 2.088, this one and this last one. Okay, so we can ignore this one as it is far away from the imaginary axis. So on the basis of this remaining two roots, it can be termed as an overdamped system, as both the roots are real and negative and no imaginary parts are there. So now we have to check the response of the system against the step input. You can see here step input is nothing but it is a trigger pulse which is given at the value of 1. Okay, you can see here at 0 step is given, so it will increase from 0 to 1 and it will become 1 for steady state. Okay, and you have to see the time response of that. So this is the step input, this is your system time response. So it can be seen that the response has no oscillations. Okay, when if roots are complex, suppose if roots are complex, then the response will exhibit or include oscillations. So roots are real, so no oscillations right now. So but the overdamped system has a damping more than 1. Okay, so damping is more than 1. So now, so in the presence of open loop transfer function, okay, this is what k the value is. So gain margin, after finding out by using body plot, it's 29.5 decibel, phase margin is 81.5 degrees, and we know that gain margin is nothing but it is the value of gain to which the system will remain stable, and this is the value of phase to which the system will remain stable. So also it should be noted that, okay, while designing any control system for this plant, overdamped system means this kind of systems are not preferred because roots should have slightly imaginary parts. Okay, so in case of overdamped system where damping is more than 1 but damping around 0.8 is preferred, okay, in this case. So we have to take a different value of k. So we have seen the system response at 0 k equals to 0.2. So lesser the value of k, the system will be more stable, but steady state error is high, okay, in this case, and there are no oscillations because it is overdamped. So as we increase the value of k at 1, so in this case characteristic equation by replacing k will be like this. Okay, just k is been replaced by 1, and roots are this one, 2, and this one. Okay, so there is one imaginary pole, okay, for this. By using synthetic division we have find out one complex pole, so we can ignore this one if we want because it is not on the imaginary axis. Okay, we have to consider this one. So on the basis of remaining two roots it can be termed, so there are two roots in this. Okay, so first one is plus, second one is minus. So it can be called as undamped system, underdamped system, as both the roots are complex and having real parts. Okay, so against the step input the response is given. Step input is given at 0, it will go to 1. Okay, so now this is the time response of the system. So you can see here, as the value of k is increased, the stability has reduced a bit, but steady state error has been reduced at all. Stability is reduced but steady state error also reduced. Okay, it is taking a longer time to reach the final value. So open loop transfer function is after finding out we can just replace by k here 1 and s plus 1 s plus 2. Okay, it's not given here but we can assume it, and gain margin is found by using body plot. Phase margin positive, both are positive, so system is stable. Okay, so the last value is for k is 5.8. It is the highest value. Now we have to see how the system responds to higher value of k. So we know that this is very close to 6, so you can understand the system is quite stable because higher the value of k, higher the system will be go into the less steady state error. Okay, but almost on the border. So now roots are given as like this. These are the three roots. Okay, both are in which two roots are complex, one is real. Okay, so now you can see here the response of this system. So for a step input, the system will oscillate or produce offset in a large manner. Okay, time response we can see here, there are a lot of oscillations because of the higher value of k. Okay, so the open loop response is given as like this. Gain margin is 0, okay, near to 0. Phase margin is also 0. So it can be analyzed from the previous cases at k equals to zero point 0.2 and k equals to 1. Gain margin and phase margin are reduced in this case when k is greater. So because the gain margin and phase margin are near to 0, which means it is marginally stable. Okay, if both are negative then it is unstable. So because of this the system is marginally stable and the steady state error is also high. So we have to choose the value of k which is suitable for the system, which will produce more stability, less steady state error. Okay, now we are going to have a look on the next controller, that is integral controller. So this integral controllers, it will produce the output which is proportional to the integral of the error. Okay, it is also actuating signal. Okay, and now let us analyze the controller mathematically. This is the output which is directly proportional to the integral of the error. Okay, so when we remove this sign, this is what the constant is, we can find out the ki, which is the controller gain. Integral controller gain is ki, which is integrally proportional to the error signal. Okay, this is also called as a reset controller. So there are different advantages of this controller. So it has unique ability. This controller can return the controlled variable back to the exact set point. Okay, and with the exact set point following a disturbance, that's why these are known as reset controllers. Okay, disadvantages are, because of this controller, introduction of this controller into the system will become unstable because it respond very slowly towards the error. Okay, next one is the derivative controller. So derivative controllers are the controller which produces output which is proportional to the derivative of the error signal. So derivative controllers are the controllers which cannot be used alone. It should be used in the combination with P or I. Okay, these are because of disadvantages, like it never improves the steady state error. Okay, so as steady state error is high, stability is less, so it's not able to use alone. It produces saturation effect and also amplifies the noise signals produced in the system. Okay, so this is the formula for derivative controller. Okay, which produces output proportional to the derivative of error signal. So when we remove this proportionality sign, it will become kd. Kd is the controller gain. Advantages are there for this controller. It improves the transient response of the system. Okay, so the time required for system to reach from 0 to final value will be smooth. Okay, now we have to choose the different combinations of controllers. Okay, now we are going to study the combination of proportional and integral controller. Okay, these combinations are used in order to improve stability and steady state error. Okay, so alone a controller cannot produce the desired characteristics. Okay, we have to choose the combinations. Okay, so it is a combination of proportional and integral controller P and I, yeah, which is equal to the summation of proportional and integral of the error signal. Okay, so we can see here the output is proportional to the integral of the error plus proportionality of the error. Okay, so after removing this proportional sign, we can see here the output is the product of integral portion of the error plus directly proportional to the error. Okay, where ki and kp are the controller gain. So now we can see here the connection of that controller. So this is your proportional controller. Okay, this is your integral controller. This is the integral of the error. So their summation point is used, which is output is given to the system. Okay, So you can see the time response. The response shown in this figure, okay, with k and ki values, okay, different k values. So proportional value is chosen to be large, that is 5.8. Integral value is chosen to be very less, 0.2. This is the time response. There is a large offset. So in this controller we are adding one pole at origin and 1 0 somewhere from the origin, okay. So as the pole is in origin, its effect will be more, okay, because of which PI controller may reduce the stability. So this controller has an disadvantages, but this advantage is that one advantage is there, that is reduces steady state error drastically. Due to this reason, this is most widely used control, okay. Now we can see here earlier we have analyzed the P controller, in which it is just to the merge of instability. So by adding this Ki proportional integral value, it will be more unstable, okay. So the integral part reduces the stability, but which does not mean that the control system will be in the unstable region all the time, okay. So in this case of PI controller, we have added an integral part and the system will become unstable, okay, for this controller, but steady state error is reduced, okay. Now as the disadvantages are there for P and I controller, we are going to switch to the P and D controller, okay. So we will see this PD controller and then PID controller in detail in the next lecture, okay. So till then watch this video, and if you have any doubt you can ask me regarding the P and I controllers, okay. So have a good day, and we will end this lecture here, okay? Bye.